Okay, so our door is closed, so I assume that we can all start. So thank you for coming for the workshop or tutorial, whatever you call it. So this workshop, we'll have, first of all, we'll have a break in the middle. It will be around 30 minutes. I will try to be stick to the schedule, have a break around like 10:30, but it really depends on the pace of like how people are feeling and stuff. So if you need a break or anything, you don't have to wait for that break. You can just like go get a coffee or use the bathroom if you have to. Don't worry about that. Another thing, because I think I've already sent a message about where you can find all this material and slides beforehand, but if you haven't get the time to check it, don't worry. This is the link. So it's on GitHub. So it's on my account, and it's called Using Numba. So if you go to that repo, you can clone it. You'll have all the Jupyter notebook that you need, and also there will be a link to the slide deck as well. So that's the kind of what I want to say beforehand. Also, I'm Cheuk. I work for Alaconda. That's why I work with the Numba team. I don't match with them like physically, but I do talk to them regularly. So kind of, if you have any questions, I will try to answer. If no, I will direct you to them direct the question to them for answering. I love open source. That's why I have been, getting involved in lots of open source projects for a few years. And also I organize events. But I don't want to, tell you about all these different events you can go to because you are now just started at a very amazing one. So you can enjoy PyCon US first. So I want to know what's people's background a little bit first. So who is actually consider themselves data scientists and handling data and doing analysis of data? 1, 2, 3, some of you. So what do other people do? Are you a developer that just write code and you are curious about Numba and what does it do? Okay, so maybe we all have the same problem that we think our code are too slow and we want it to be faster. So for today, I'm going to mainly explain Numba. So Numba is actually designed to use. I can show you later. So yeah, Numba actually is designed to use with a lot of data science work. But if you're curious, there's other things that also do similar things that can compile code. I can tell you a little bit more later if you found that. The exercise today is not very applicable to your work because you don't work with data. It's fine. I can also give you other recommendation to other tools that you may try out. So for those of you who are mainly doing statistical analysis, doing data science work, it may be a little bit new to you. What is profiling? What is compiling? Why do we care about that? Because I just, day to day, you load in some data through maybe pandas, CSV files, and then you load it in, you do some data kind of manipulation. Maybe you deploy some scikit-learn algorithm, and you get your result, and then create a beautiful dashboard or story to tell to your teammate or your boss. Then, well, we're all happy. Why do we care about this? So. If your code is too slow, a lot of times you may wonder why is it slow, right? Why it got stuck. So, profiling. I know some of you who are maybe you're a software developer. If you come from a computer science academic background, this is all trivial to you. But I'm just going to get everybody in the same place. So profiling is actually we are investigating what our code is doing, right? We call that dynamic analysis because there are different ways you can analyze your code, but how profiling do is that actually some kind of tool that is running along with your program and then kind of inspect what it is doing when it's got executed. So those are called profilers. There are different type of profilers. I have also a few days ago I was in PyCon DE and I give a talk about memory profiling, which is another type of profiling. Today, we care more about the speed. So there are tools that do that, and we want to investigate because we want to know which part is slow. Maybe we can improve that part that's actually slow. So compiling is another tool, kind of things you could do to improve your speed of your code. So for those of you who is like maybe from a science background, from another background that is not computer science, then you may heard about the term compiling a lot, but you don't actually know what it does. For some programming languages, compiling is required to execute your code. Python doesn't work that way, but there are other programming languages that work that way. So compiling is actually because your computer actually, they're dealing with 0 and 1s, right? So they can only understand things that are low level, which is, for example, machine code. They're basically numbers. They're 0 and 1, so your machine can understand. But that's nobody wants to write code in machine code because it's so difficult. So that's why we want to write in a programming language that can be compiled into a model level code that kind of, is like a translator who translate a piece of article, like a Google Translate, from a foreign language to a language that you understand. So compiling is translating that from a human understandable one to the machine understandable one. Without doing that, like I said, Python works slightly differently, but for other programming language, for example, C, C++, the program needs to be executed before it can be, the program needs to be compiled before it can be executed. So sometimes you may actually heard people talk about that for beginners. Actually, C and C++ is very, a little bit difficult to learn comparing to Python, because every time you make some changes, you have to compile the code before it can get executed again. So if you have a huge chunk of code, as I remember my time in university, that the C++ course, they teach us C++ for the first programming language. Scary. And then you have a lot of different files. If the program is big, then you have to compile all of them and then run. It's so super slow to kind of test things out. So, but there is a good thing about compiling is that once you compile the code, it's actually because, it's already in a form that the machine understands. So actually, it can be very fast. But Python doesn't do it like that. So again, we are here. We want to make our code faster, especially doing data science work. So this is the strategy that we're going to deploy today. We'll analyze what makes the code very slow. So at the beginning of this workshop, there were, unfortunately, there's a lot of concept, a lot of things like how to use number and all this. I need to clarify first through the first few exercises. And then after, you get a chance to get your hands on to a final big project that you're trying to improve the code. So this is your strategy, right? You can analyze it, and then you see which part is slow. You try to make the slow code faster. Sometimes compiling is not needed. For example, Numpy, because it's already have a lot of optimization of itself. Then what it does is that if, for example, if you have used Numpy, you know that avoid element-wise operation, try to use matrix operation because Numpy is optimized for that. So that would make your code faster without using number or any other things to compile your code. But sometimes, even you try to avoid all the slow code, sometimes it's not avoidable, then compiling may actually help you. But how, then I will go into the detail later. So Numba is a JIT compiler. So again, at the first half of the workshop, a lot of concepts need to be clear, right? What is a JIT compiler? Scratch your head. What is JIT? But what we can get from this definition, which I copy from the documentation, is that we know that it's work for NumPy, so it's very good for a lot of numerical code because a lot of numerical code actually use NumPy, so it's kind of designed for that. It translates a subset of Python code, so translating code, something to do with compiling. Well, compiler already told you that it's doing some compiling, but that's what it does. And so your code will be, a chunk of your code will become low-level code, which is faster. So, but what makes it different from the compiling that I explained earlier? What is it different from, for example, C or C++ that you compile the whole program? Is that is a JIT compiler. It's not just a compiler. So JIT stands for just in time. So I found this term very funny, and once I know what it means, that I use it in my daily life, I'll be like, oh, just in time finishing a presentation, that kind of thing, which means that it basically finish it last minute when it does compiling. So, it's getting more questions than answer right now. Because how Python works is that Python does not compile the program. Like I said before, you don't have to, write all your Python code and then run some command to compile all your Python code, which is maybe something.py, into a low-level code. So Python doesn't work that way. Python is actually an interpreter. So for those of you who have not thought about that before, Python that is on your machine, it could be, for example, you download it from PyPI, or maybe you get it from Anaconda, there's a Python inside. So that, Python itself, we all know is a programming language, but that thing that's in your machine, that is actually an executable file. So it's actually a small program in your computer that interpret your Python code into code that the machine understands. So, for example, CPython is actually interpret Python into C, and then C, of course, can be compiled into lower level code, so your machine will understand those C code, and it will understand your Python code. So it takes time. So Python, that's why you have heard a lot of people say Python is slow, right? Because every time you have to go through these steps of CPython, Python, if you use Windows, actually it's python.exe, so it's an executable file. It will see your code, and then it will pass it to the C APIs, and it will and then it start to work. It's slow. It's not like for example, you write a program purely in C that before you run it, it's already compiled. So every time you run it, you run that compiled form. So it's super fast. So how can this compiler kind of modify the behavior and to make things faster for ourselves? Is that when you'll see the code later, you can define this part, I want it to be applied, to be compiled. And every time the Numba or other JIT compiler see that bit, and then, if you're gonna, the first time we saw it, for example, in your definition, it's not going to do anything yet, but until that part, that function is get called, then it knows that, you are not writing things for nothing. You're actually using it. Okay, I'll compile it for you. So next time you use it, it will be faster. So that's the magic, right? So remember one thing: when the JIT compiler sees your code that want to get executed for the first time, it will compile it. Okay, so what does that mean? It means that if you just use that function for the first time, you will go through the step of the compiler will compile your code and it got executed, right? But the second time, when you call that function again, it won't compile the code again because it's the same thing, right? You haven't changed the definition of your function. It's going to be just the same thing. So it got to look for the already compiled code and execute that one. So it means that the first time and the second time, when you call that compiled function, the speed will be different, okay? So bear that in mind, because that will be useful in our exercise later. And that's also explain why a lot of times, people just use a JIT compiler and stuff, and it may not speed up your code, but if you have a loop that you actually do the same thing again and again and again, then that would actually help you. So be smart, don't use the JIT compiler for things that are not looping, because then that may actually be slower. So, with Numba, so Numba is designed for NumPy. Like I said, it's designed for the scientific kind of coding. There's another thing you may have heard about called Python. Python, again, is a JIT compiler. It will compile your code. That is more kind of, I would say, more general. And actually, a lot of your the thing that you use, for example, Panda, actually under the hood, it uses a lot of Numba because it will help, pandas to be faster. And for example, scikit-learn, also use a lot of Python. It kind of help the algorithm to be faster. So, so Numba or Python, they are all like JIT compiler, and they have been used in other libraries without you kind of knowing. So it's actually there everywhere. And so Numba, again, like I said, because it's JIT compiler, it kind of, for things that loops, is where it shines. So if it's, again, be smart, think about when you use it, where you use it. So in Numba, there are different modes that you could use. So ideally, you want everything to be no Python mode, because I think now you may already understand Python is slow, so we want to avoid Python. So using no Python mode means that everything that is defined in that, all the code that you include into no Python mode should be compiled into something that is low level, that is, it doesn't go through the Python C API, which is the interpreter that I talk about. It will see your Python code and tell the C API to do stuff. So we want to bypass that. We want to directly compile that bit of the code, and then it will get called directly in like very fast speed because it's a low-level code. Its performance is very good. If you can make all the things no Python mode, then you would probably have a very fast time with, if you don't count the compiling time. But it's not always the case, right? Because a lot of number things, a lot of simple calculation, you can use no Python mode. But we all have been there, right? We have used different Python objects to do different things. So those Python objects, if you are using it, then you can't use no Python mode because they are Python object and Numba doesn't understand. So you have to use something called object mode, which is it can still have some capability of handling Python object, but for the bits that it sees that actually you can bypass it, it will bypass it. So it's kind of a middle ground between not doing anything and using no Python mode. So it sometimes kind of make your life easier, but then you have no control of what is actually being done. So this is, you'll see the syntax very soon when we go to the Jupyter notebook. So to use Numba, we just call in the decorators. So there are two decorators, JIT and NJIT. So NJIT means no Python mode. JIT means, well, by default, is object mode. But you can also, like here, you see that actually you can also change JIT into no Python mode. But sometimes if you use everything no Python mode, instead of typing so many things, you can just call it an NJIT. So yeah, I've already covered this. Ideally you want everything to be no Python mode, to be have optimum performance. But a lot of times, you may accidentally or under the hood is using some Python object. Then you can't avoid that. Then maybe to make things work, you just switch to object mode. So there are other things that actually Numba would be very useful as well. For those of you, for example, you work with a cluster, you work with the CUDA GPUs, or you have a CUDA GPU at home, then you may wonder, okay, does Numba help me? Because Numba does support CUDA GPU, but I'm not going to cover it today because not everybody is using a GPU, CUDA GPU especially. But there's talk that actually talk about that in detail. If you those of you who use it and you wonder how you can use it together with Numba, that is the place that you could look into. So I think I talked too much, and so we better look at the notebook and do it together. Like I said, there's a lot of things that at the beginning, there's a lot of concept we need to clear about, so unfortunately you have to hear me talk a lot, but after that there will be a chance for you to kind of code and then try to in a similar kind of setting of when you're working and stuff. So get the repo and then read the by the way, the Wi-Fi is already there. I hope you already discover it before I start talking. Always have the documentation ready. It's very useful if you have an error, you don't know why it's like this, and you don't understand how it works or how to, even the syntax. Then just refer to the documentation. It's fine. So in the notebook, you have a few things. Ignore the others. Well, maybe have a look at README if you just downloaded it. But otherwise, other things, you just need to worry about the notebook. So I hope you already have the capacity of opening a Jupyter notebook. There are a lot of ways to set it up. For me, because this is my personal computer, I just set up myself, install Jupyter notebook, and install these things by pip install. But if you don't want to, set up yourself, you are already, using Anaconda. Anaconda will have all of them included as well. So let's open the first notebook. We'll do it together, and then we'll read the code together, try to understand what's going on here. So far, any questions? I talk too much. So any questions? I want you to talk. No? Yes, no? Okay, all good, following? Good. So, this is the exclamation mark magic. It just means that you can execute some kind of command on like a command prompt. So if you haven't got like Numba and Numpy installed, you run this cell. But if you have installed it, this is useless for you. So don't do anything about it. I'm just skipping it. So this is kind of like demonstrating how Numba works. So like I said before, there's JIT and NJIT. They are decorators that you could import from Numba. So the decorator would decorate the function, and then just basically is marking that Numba will understand that bit that we want to compile. So so you have to, so first thing, I think like people asked me before, that's like, oh, what if I have just a bunch of code? Well, you have to wrap it in a function. Because otherwise, I don't know, like, can you just like kind of turn it on and off? Maybe, but the most, official way to do it is to use the decorator. You have to wrap your process, your calculation, whatever, in a function. So we are also doing some timing here just to check, like, comparing the time with or without the compiling. So this is doing something very simple, right? You just have a huge NumPy array, and then we will just do some kind of calculation with it. And so these two functions are basically the same. The only difference is that one of them, we would modify that function by applying a decorator, which is the JIT decorator. And we are using no Python mode, so you can actually change it if you want. You can change it to NJIT, and then you can change it to NJIT, and then delete this. This will be the same. All right, you can try both, but I would just stick to the original one for now. They are basically the same, like I said before. So that's right. This is an experiment, so there's not much we can do, but we can look at the result and try to make sense out of it. So which one is the fastest? Which one? I think it's quite obvious. Oh, you can look at your machine. Your machine may be different, but it should give the same result. Who get the without compilation the fastest? Let me know. You have the without compilation the fastest. Yeah, so you can see it's very interesting here. It's like with compilation and then after compilation. Why there's like two different things, right? We are comparing the one with the JIT, one without the JIT, but why there's two here? So if you look at the comments, it's already trying to explain it. So without compilation is your baseline. So it's like what you normally do with like Python doing Python thing. You don't interrupt it. You just let Python be Python. So this is the without compilation time. So you can see they are at the different of magnitude. So be careful when we do this kind of experiment. Be careful of like what scale are you looking at. So you can see the first one and the last one. Actually, they're comparable, but the last one is actually kind of 1/3 of the time that it takes. Maybe half. Let's say it's like half the time, which is like double the speed. So. But the one in the middle is the puzzle that we have, right? Like, why this one is so slow? It's like, order of like 5 is like slower. It takes like, how can it's like 10 to the power of 5 times slower? No, actually 10 to the 4 times slower, but it's very, very slow, the one in the middle. So what happened? What happened is that if you relook at the code, right? So this is without compiling. This is Python. Is okay, fine. So this is the one that we are using go fast, which is the one we add the JIT here. So this one is supposed to go fast. Why is this so slow? The reason being, like the opening, I already planted the seed in your head that compiling is slow, and because it's a JIT compiler, it doesn't compile this bit of code beforehand, right? When you execute it, so Python is reading, it's like, okay, I'm trying to talk to C API, try to get your thing done. So until here, it's like, oh, now Numba come in and say like, wait a second, that is the JIT, so that's like me doing my thing, now I will compile it. So okay, Python say fine, okay, Numba compiled it. But compilation takes time. So this one, that's why it takes so long, because it's compiling. So for example, if you only call go fast once, so what will you do is actually have a slower program than the original one, than the normal one. So this is not a good thing. However, if you call go fast the second time, since it's already compiled, so again, Python read all the code and then go here and then Numba jump in again and say, hold on a minute, this one I have already compiled. Just grab that already compiled things. Don't need to talk to the C API anymore. So it's like, okay, so execute that super fast, right? Yes?
So if this is compiled in like a certain scope, does it apply to the outside of that scope? Use the function again, or is it only that?
No, it's only that bit. So that's why you have to wrap the bit that you want to speed up in a function and then apply a decorator to it. So for those of you who are maybe new to decorator, this add thing is actually would take what it decorates, which is a function, and then modify it, right? So, well, normally you can write a decorator and modify it using Python code, but this time, of course, Numba is doing the Numba magic, right? It will come in and modify it and make it into another blob of things, which is the compiled code, and then it will get referenced. So next time when Python see it, it won't talk to the C API to try to do what it normally do, but that will try to call that already compiled bit, or if it's the first time, compiled it. So, yes, questions?
The first time go fast is called,
Mm-hmm.
X is, you have only integers. Suppose that you call the first time go fast with X has just integers. The second time you have floating point numbers. Is it going to be fast?
You mean
Second time
comparing?
you can't go fast.
Mm-hmm.
You have the same X in terms of size or whatever.
So,
Suppose that you have floating point numbers. What are you going to do?
so the difference. So if you're asking what's the difference between the go fast calling first time and the go fast calling the second time?
Yes, the similarity will be.
So if you put in a, so you put in a different X, you mean?
Yes, that you provide floating.
You are very ahead of our time because no, it's very good question, because there's you have very good thinking. That's why you already see the problem that we may encounter in the future, right? So you will see later when we go to chapter 2, sometimes we would come into some problem. Is that because Python do dynamic typing, right? So in Python code, this input can be anything. It could be integer, it could be floating point, it could be imaginary number even. But for ngJIT or the JIT no Python mode, it doesn't work that way. You need to have a defined type. So that's why if you like the scenario, you suggest that, oh, what if I put another X in go fast the second time? What if it's a floating point this time? Well, it won't happen because we can't compile it if that's the case. If we don't know the type of the input, then it can't be compiled. We will see that problem later, then it will make more sense. But it's very good that you raised this question, because all of us will have this question later. Okay? It's very good. So now we have the basic understanding. So this example is just to explain that what it's actually doing, and the first time actually is slower. So we have to remember that is the main thing that people got confused when they start using Numba, and that's why they think, oh, it's not really helping me. So it may be one of the reasons why. So now we are learning something about not just Numba, about NumPy as well. So like I said before, NumPy is designed for numerical calculation, especially for matrix calculation, right? So we are now, so in this experiment or example, we are creating a NumPy array that's quite big, okay? So we are doing some calculation with it. So this is a something with sine and cosine there. I don't like the name of this, like it's some trigonometry thing, right? Like, like the triangle, you calculate that, the tangent, whatever, the bit. So I'm not going to explain the math. But there are multiple ways of doing this calculation. So for example, the first one, I'm using a NumPy operation, which is basically for example, x, if x is a NumPy array, I would just use the NumPy method, the sine and cosine there, and do the calculation, instead of the second one here. So I would run this. I know this is out of order, but I will run this code because I'm explaining this one. So this one, I'm doing a loop. I'm doing element-wise operation. So the difference is that this one, because this np.cosine and np.sine, they are NumPy methods that is built to handle NumPy array. So you don't have to worry about each element in this array. It will just handle it by itself. We don't know what it does. Actually, we know, but I'm not going to show it yet. So this is if you don't understand NumPy. If you think about it in a more more deep dive way, it's like, wait a second, I have to calculate it one by one, right? Because it's a matrix, and it's very complicated. I want to do it one by one, so just so that I am in control. I know what's going on. Okay. So if you compare these two, you already see the warning. It means that this one's quite slow. So I'm going to explain a little bit about what's going on, why this one is way quicker than this one, because in NumPy, it uses not just Python, right? So if you do this inside NumPy, it won't do what you think it's doing. So you may think, oh, NumPy is calculating it element-wise, it's just a shortcut for us to use this, make our code cleaner. No, it's more than that. NumPy will have some already compiled component. They are low-level code, they are not written in Python, and it will just make this calculation way faster. So that's why in NumPy, a lot of times, people tell you, do matrix operation, don't do element-wide operation, because they are super slow. You see it's still running. That's slow. Because if you do this just purely using Python to do this element-wise operation, and Python is very slow. And you are looping it for a lot, because this one is 1 to the power of 7, so it's actually a lot of numbers that we are looping, doing it one by one. It's very, very slow, and you want to avoid it. But why do I talk about that? Why do I talk about element-wise operation? It is because sometimes, so this one, we already have a very nice NumPy built-in method that can handle it for us, so we don't have to worry about it. Just do the NumPy way, and we will get it done. But sometimes you want to do something that is maybe a little bit specific, that it doesn't have a NumPy operation that has to do that for you. You have to do it element-wise. I can't think of a very good example on the top of my head, but sometimes, for example, because there's always a way that you could, do some smart thing with NumPy and get away with it. But for example, you do very, very strange things that you compare to an array, and then you do a Fibonacci number, whatever that is nobody do that except you. Then it won't be in NumPy. You have to do it element-wise. You have to do it yourself. So you have to write it like this yourself. So, oh no, this time, you see this is 10 times slower. This is millisecond, right? This is second, so it's already 3 zeros slower. So it's very, very slow. But sometimes you can't avoid because you're doing some very, very specific things, and I need to do it element-wise. But I don't want to have a program that basically run overnight, because every time I run an experiment, I change something that would cost me a day to run, which is bad, especially for data scientists. Because, sometimes we have projects that you have to have result within a week, within a month. Oh no, don't have that time. So what should I do? So you see that now we're using ngit. Basically, it's the same thing like we do before, no Python mode. Okay, just to show it can be done differently. If you want, you can again change it into no Python mode if you want to try it yourself. So this is element-wise operation. Is stuff that this is not error. Okay, sorry, confused a little bit. The element-wise operation is here, down there, loops. Those are element-wise. So let's try to use Numba to see if it will help us to be faster, right? Because every time there are things that are slow, it's I would use Numba. You see that we try to run it first, because again, if we time it the first time, You can actually try it. You can try not executing this, well, you have to restart your kernel, but you can try. If you haven't done it, you haven't run it, you can try running this one first, and then you can like do it again or like run it 2 times. It will say that because the result, if you forget to run this one and run this one, the result will tell you that, oh, actually the result is a bit strange. The first one is super slow, but the mean won't be correct because the first one is slower than the rest. So it gives you a hint that, oh, I haven't compiled it yet. But this is the speed when it has been compiled. So it's quite an improvement, 124 compared to 200. So it's a slight improvement, but it's an improvement, good. We love it, we love seeing improvement. But this element-wise thing, right? This thing that you try to avoid very, very hard, but sometimes you can't avoid. Now, Numba is going to be a Superman and come and save you. So let's compare this to the one before. This cell, I give you a warning that it takes a long time to run. But this one is still running, but already? Yes, it's fast. It's already done. And this one is actually even faster than the original NumPy. So, wow, what happened here? Yes, it's crazy, right? Like this is, everybody use NumPy is scared of this element-wide operation. We know it's going to take forever. And now using Numba is super fast. Because, again, the magic is, the reason why it's so slow is that because it loops for a lot of time, right? Remember how big it is. The bigger your array, if you do element-wise, it's each one of them. So this one got 1 to the power of, 10 to the power of 7. So if you do it one by one, it's very slow. It adds up, even if it's not, even if one of them is not super slow, but it all adds up, right? So if one of them is improved by, let's say, half the time, it's already saved you a lot of time because it has got compiled and it's super fast, right? So it's a good thing. It's a good thing. And next time, if you're stuck, right? If oh my God, I have to do element-wise operation in NumPy, like I have to loop, or even you have to loop a lot of things, right? Like for example, calculating for example, you're calling the Fibonacci or whatever that, you have to call a lot of the function, lots of time. Then this is here to help you. So. The rest of this notebook is going to tell you all these kind of smaller things. So those 2 that I talked to you about, the main key takeaway. These are the small things that you can improve a little bit more. Yes?
The main takeaway is it will help you when you write the loop yourself, but it won't help much if you don't write the loop.
It will still help. If you compare these 2, it will have a slight improvement. It won't go slower, but unless you have to compile it the first time, then it's slower. But you will still get generally, after compilation, you'll get an improvement. But if it's not a loop, then, you have to compile it, and you may as well not do it. So yeah, loop is where it shines the most. So try to improve it when you have to loop, or, yes. Yeah, so.
Suppose that you have billions of entries. It will take you an hour perhaps to run. Because when I look at it, you run it the first time with the same array. Go. It takes you a second and a half here.
So.
Suppose that you have billions of entries. You cannot afford running for the first time without timing it. Or let's say to optimize Numba. The first time you compile compilation, the second time you are going to take advantage of the knowledge that you have of the arrays and things. What do you recommend?
So I think there's multiple scenario that we're encountering here. So for example, let me clarify, because now we are learning, right? That's why we'll compile it first and then run it. But in a practical scenario, you won't write it separately. You would just, like, for example, you have a loop. You would just call it, because you don't, we don't, how can I say, we don't actually comparing the actual compiled and the non-compiled version. This is, in a teaching setting that we do that. But if you, for example, I have this piece of code and it's in my project and I have to make it faster, you just apply this ngit and then run it. You won't be, I have to write it first and then write it second time. You won't. You just, for example, you won't even write time it because you just want it to be fast. And then maybe you already tried before, but in production you won't write time it. So you just run it once. For your question that, if I'm reading, for example, I'm reading a lot of things, I'm processing all this data, then how can I be faster? Well, so again, you can think of this as the case of element-wide operation. For example, each row is an element. Then you could actually, compile handling each row. And then every time it will be like very fast, each row. But we have to be careful because, again, Numba is designed for NumPy. So it's not designed to handle I/O, which is reading the data, those kind of things. It really can't, because I/O is a thing that Numba is not going to be speed up, because that is a Python object, and those things, like, it's not what Numba is designed for. So, and also a lot of times I/O is more complicated. It's not just how your code work and stuff. It's also about, like, how your computer file system, all this more complicated stuff. So we are trying to speed up the internal part, but not the reading and output the data part. So so there's multiple things. I know it's very complicated, and you're thinking, if I work, how can I use it? So hopefully by the end, when we try to use it, then it's getting more clear. So these are small things that you could use together with what we just explained and make it go fast. So, what is fast math? What is this swing? Scratch your head. This is kind of a case that I would see that it's not being used a lot, because a lot of times it's a very, very minor thing, that kind of smoothing the edge or something like that. Now, what happened is that for this computer, this chip, and how they handle mathematical calculation, there is a compliance that they follow. Reason being that, because your computer or this memory and stuff, they are finite, right? So if it's not handled correctly, you may accidentally get wrong results because the digits are overflowing, all these things that I'm not going to explain in detail again. Like, you can read it yourself if you want, but it's a very complicated thing that someone have a PhD published, so I'm not that smart. So what happened is that if you use FastMap with ngit, it means that we'll relax this compliance, meaning that we are not following this. But why do we do that, right? Because sometimes following the compliance to make sure that all the precision, sometimes, a float number can have a lot of precision, right? Sometimes we don't need all those digits, right? At the end, for example, when you report your result, you truncate it anyway. So all these digits at the end, you don't really care. So what you can do is to use FastMap. You release that compliance. It may introduce, in a very unfortunate case, it may introduce some small error at those digits that you don't care, but you don't care anyway, so it's fine. But by releasing this compliance, then we don't have to follow the rules of, for example, doing this operation first and then do this, then you won't have the precision error. But FastMath kind of, we sacrifice the decision, but to increase speed, because we don't have to really follow the order. We can just do whatever the order is the fastest for the computer to handle. So this is a small demonstration about how it can be faster. But again, for me, I see it as more like a kind of last bit of things you can do, because it does improve, but it's not the major improve, like, for example, the looping things that we showed earlier that can do. So so this is comparing using FastMath and not using FastMath. So they are both using ngit. They are supposed to also do the sum very fast. But if we relax the compliance, which is using FastMath, then it's slightly faster. So you can see that it's like 5 milliseconds faster. Like, it's not a huge. It's not like multiple improvement. It's a slight improvement. for if you, again, looping and doing a lot of arithmetical calculation, then your computer, if they don't have to follow the compliance, they can just do it as fast as they can. It will be slightly faster, but this is the last bit of improvement that you want to do. For example, you have nothing else to optimize, right? You have already done a good job. You want to just go through the finish line and do it a little bit better, then you can maybe think about whether you can use fast math. Another thing that you could improve is to use multiple cores. For example, my computer nowadays you can easily get a computer that has multiple core. If you do something on your cloud service, you can also use multiple cores, so it could be fast. When I write this tutorial, I was still using a very old dual core thing, but you can still see some improvement. So if I run it now with this new computer, it should be quite good. So. 46 before is 130 something, right? Yeah. So this one is the same thing, cosine, sine. Remember this thing? So if we use, so my new computer is 8 cores. So if you compare 1 to 4, this is without the multiple core. This is with multiple. So it's kind of like 1/3 of the time saved. So yeah, it's kind of 3 times faster, right? So. Python by default is not multi-core, it's not multi-thread. Python by default is single thread. So by using this, we would also, I don't know what it does, maybe remove the GIL, I don't know. Then, yeah, it would be using the power of a multiple core, so get faster.
When would you not want to use parallel then? It seems like you always
I would say sometimes you may come and I can't think of a good example again. But some algorithms that multi-thread actually can damage the result. Yeah, because it's kind of similar to the concept, right? Like fast math, it has to follow certain order to make the precision. But for some other algorithms, for example, like parallel would actually mess things up. And sometimes, the scary bit is that it will mess things up and then you don't actually know that it got messed up. So you get the wrong result and then you thought it's right. So yeah, for this thing, this is demonstration and we all know how it works and that's fine, but be careful. Yeah.
What's the difference between input line 19 and line 20 where you're compiling it as like a singleton in the notebook and then you're actually running time it that actually fully evaluates it? Is it just like getting the prepper in the first one and then actually fully running it? Algorithm? And then which one, where is it doing the just-in-time compiling those lines?
You mean like this one or?
Yeah, the difference between those two statements. Because it's running the same statement except it's doing timing. So it's
Yeah.
evaluating the complete array in the second one and just the
Yeah. So actually I can quickly do a experiment if you allow me. So I can restart the kernel. Okay, restart. So go back to original state, and then we try to quickly want to run some of the thing that I need. For example, I need to import whatever things here. Oh, I need this probably, and then okay. So yeah, I think I have the engine and JIT, right? I'll run a few of these. Oops. Yeah, engine is not defined, so I'll run of these. So okay, now let's go back to here. I think it should be fine. So I'll have these parallel run. So I created this. And I don't compile it this time, I jump directly to this one. If I run it, yeah, you will see that what happened is that here is, actually it's not, maybe it's strange because, yeah, it doesn't show. But anyway, this does is that it will compile, so maybe I have some previous memory of this, so if you have to go back to maybe restart this notebook or whatever. So yeah, what I want to show is that if I run it after I've compiled it, because the first one is always slower, right? Like, for example, go back to this example, you see that this is doing the same thing, go fast, right? So the first time is always slower. So when I want to compare the results, it depends. Sometimes you may be like, oh, I want to see actually, right? Actually, when I run the code, how much it improved. Then you may want to include the first one because the compilation time should be taken into account. But if you just want to do a pure comparison, how fast it is by compiling it, then that's why in this notebook we always run it second time, because the first time we want to exclude that, right? But yeah, I don't know why it's not showing, but like if you don't run this cell, if you directly run it, it should show you that, the result is a bit strange because, the first one is actually slower. They will tell you that, the deviation is very big because of the first one very slow, something like that. But yeah, mess around with the notebook. You may be able to see that, strange things yourself. So, yes.
I know this is probably only for, like you said, math and stuff like that, but have you tested within the parallel input outputs? Like in every, the statement would read something from input output. I would think probably with the parallel, if you have like function reading from outside, might be actually faster than reading it without that node.
Yeah, that's something that I think is worth trying. I haven't tried myself. Again, I don't know if Numba is going to work in that scenario because probably if anything involve I/O, you can't use njit mode. You have to use the object mode, which is just the JIT. But yeah, multi-threading practically is supposed to be faster, right? But for example, I/O, that kind of things, then you also have to use a tool that is also be thread safe, because especially when you're accessing the same object with different thread, and weird thing can happen. So I would say that you can look at Numba, but also maybe look at Python. Maybe they know how to handle it. I haven't used Python for ages, but I've just talked to the core maintainer like a few days ago in Germany. So yeah, if you encounter him in a conference, then you can maybe ask him like, oh, is it thread safe? But yeah, I think but also so my talk tomorrow, we talk about sometimes scientific programming, do we get the improvement of using multi-thread? It depends. So come to my talk tomorrow if you want to talk more about multi-threading, JIT, and all this stuff. So that's the first notebook. Any other questions? Do you want a coffee? Do you want a break? Yes, I can see some nodding. So originally the plan is 10:30. We have a 30 minutes break. How about now we have a 15 minutes break, and then we would maybe have another break later. Okay, good. Okay, so we will come back at 10:15. Okay, so we're about to start. Before we move on, actually I have a question as a survey. So I want to know what environment people are using normally. For work or for example, this, I know that we're all using Jupyter Notebook, but so what would you use? For example, do you prefer, who do you use pip to install your things? Pip. Who use Conda? So a few of them, okay. Okay, so who use, this is very tricky. Who use PyEnv to manage your environment? Okay. How many use Conda? Okay. Oh, actually, it's quite even. Okay. Poetry. Oh, poetry is getting more popular. Okay. Who is using others that I haven't asked? Okay, I don't know that one. Any others that you use? No. Okay. Okay, good. I just want to know what people are using. So thank you for participating. Okay. Let's go back to Numba. So, okay, so so I think some of you already kind of very smart, right? Already have questions about, why do we have JIT and njit? When do we use it? And what if it doesn't work? And all these things. So we're now going to debugging or problem-solving territory. That when you start using Numba, you may come across some of these. Again, Numba is, some of you asked me so when will I use it? Because, a lot of mathematical library already optimized. I would say that for most of you, you may actually be using Numba without you thinking about Numba because it's written in some of your libraries. So I would say that the maintainers, they use it the most. But for those of you who, doesn't have plan to contribute to that project or become a maintainer, there may be one day there's the edge case that, for example, you have a thing that no library is providing that for you. You have to write it yourself, and so you also have to do some optimization yourself. Then then this is the time that you suddenly remember this, and maybe you look at this Jupyter notebook again. So it's not a very that's why it's not a very popular tool. A lot of people don't know about it, but actually they're using it without knowing. Okay, so that's why sometimes it's difficult when you encounter a problem. For example, remember when you learn pandas, you have some error message, or how do I do this? You can Google, and a lot of answers will be provided, right? Because the user base is very big. For Numba, it's a bit tricky because a lot of times, you can't find exactly what you want the answer easily. So, but I hope that by this notebook, it can solve some of the very more common problems that beginners may come across. So it already saves some of your time to troubleshoot. So now we are doing something that someone already mentioned. Oh, what if I compile the function and it's designed for integer, and then I now put in a float? So what happened? So this is the problem that is caused by the type. So in Python, types are very dynamic. You can put in anything. You can change the type, or but for program that need compiling doesn't work like that, right? If you have learned other programming languages, for example, again, C or C++, those you have to define the type of the variable. It's not dynamic like Python. So those are actually designed to be compiled, right? So it's not like Python. Python is like I said, it's interpret bit by bit, so it kind of figure it out as it goes. But for compiled program, you need to know beforehand, because the code needs to be translated into something that a machine understands. And if you can't just suddenly decide a type because it has been translated and the machine is not very smart, it's very rigid. You need to know the type beforehand. So so let's look at this. This again is reminding that ngit is the no Python mode. So we are compiling this for sure, and we're adding two numbers. And this is something that you may do in Python, right? X and Y, there may be a naughty user putting something that is not integer, or if it got passed in from another function, and then it may come in as a string. For example, if you running your Python code and then having the, when you type in the command Python mycode.py and then 1 and 2, right? So those 1 and 2 actually come in as a string. So this is what you would do. Oh, I'll convert it into integer, and then it will be fine, right? So it's fine in Python, but it's not always fine. So this is no Python mode. So this is, again, the more rigid mode that it can't handle Python object. So this is kind of working fine, because both of them are integer. It know what to do because these two are supposed to be integer, right? So everything is fine. But like I said before, if this is what it will come in through your arguments from the command line. It is a string. It's not an integer. Then you will have a scary error. You have a type error. So it doesn't work. But then you will scratch your head, right? Normally, because I have already done this in Python. Why it doesn't work? Well, because this is a compiled code. It works in Python, but it doesn't work if it's compiled. So another things you can do is to use. So this is what's going on here. So I suggest you want to be very fast, you use ngit, very optimistic, very ambitious, and then no, this does not work. I don't know what happened. Okay, the quickest fix is to remove the n. So I'll just use jit instead of ngit. Then instead of getting a error saying that no, I can't do that, Numba can't do this, Numba will say that okay, it's not recommended, but Numba will handle it for you. This is what happened. But again, this trade-off is that the code won't be, as fast as you want. So, so this is another case that we may come into the similar problem. Is that, for example, the return type. So, this is the problem that we have with a type that the input type is not what we are expecting. We're expecting integer, and now it's not an integer. This is the other side of the problem, is that what about the return type is not defined, right? For this one, what is the return type of this function? What's the return type? Is an object is a very, very good answer. You apply to everything. So for those of you who like love typing, you'd be like, oh, you would maybe mark it as union, string, and integer, something like that. But again, it doesn't, Android doesn't like it. It can't be both. It needs to be one. So this can't be done. So yeah, so we have to use a proper decorator for that. So this is your time to shine. Can you fix that for me, please? So if you have the notebook open, go to this cell. You may be able to find it using the to-do. Then can you fix this? I will give you maybe 3 minutes to fix it. It should be quite straightforward. Yeah, scary warning. I don't like it. Yeah. It doesn't mean a lot of things as well. It's like I will scratch my head. What's going on? And can't find a lot of answers on Stack Overflow either.
Oh, really?
It's not as easy to find as other things. For example, if you use pure Python, a lot of people use Python, they would answer your question. With Numba, you have to be very lucky to find someone who is expert user in Numba and answer your question.
So wouldn't best practice be to like break this up so that you have, no, never mind.
Or you can split it into two functions, right? For example, you sacrifice one value, and then that value is a error value, and then you have another function to mark it up or something. Yeah, there's always a way to rewrite the code, but it's just that, does it worth the effort? Do you want to do it? Yeah.
Because before the function, you could have like a check, right? If it's not that, then use a different function.
Yeah, you can always break it into two parts, but yeah, this is a very oversimplified example. But lots of things are not that straightforward. They're very tangled. There's a lot of loops and stuff. It's like, you will see later when we look into the scary bits. So 1 more minute. Who already? I see some of you already stopped. So I guess you have done it. So, who still need more time? Let me know. No one responds. So I assume people already guessed the result is to use to remove the n and use JIT. So yeah, so if you do like JIT, I think I've imported before, right? So it should be fine. And then if I run it, then then yeah, I get a scary warning, but it's not a scary error. So again, like this, if you don't want to see them, you can change your setting in your Python or Jupyter notebook and get rid of them, and as if everything is fine, But
It's telling you that you could add the without the force object, and then it doesn't give you the warning, right?
No, so it's basically telling you that it's not optimized.
Mine has there's a deprecation warning.
You have a deprecation warning? Oh.
There's one there too. Does that mean that this functionality?
Well, you have to add force object equals true. I think that's what it's saying. You have to call force.
Yeah, it's there's number warning as well. Add one again was compiled in object.
If you add that parameter to the decorator, the warning goes away.
Maybe there's the multiple problem here. You can see like, oh, you already compiled it before and
So
stuff like.
without force object equals true, if you add that force object equals true
Ah,
to the decorator, it'll just pass without it.
yeah. I think like now it's saying that like, well, you're kind of like forcing it. Do you really want to force it? And then you said yes, I want to force it. Then it won't want you because you already know what you're doing. Yeah, it's just in case like if if you're kind of a beginner, you don't know like you thought is this what the best you can do, and then it will just tell you a bunch of things. But if you are very because it's ambiguous, so Numba doesn't know whether that's something that you want, just to make sure you can always get rid of it if you want. So, extra task. I love extra task. So profile this tool and compare. I will give you some time to run it yourself before I run it and everybody see it. Then you can have a thought about why is it different, and yeah, what's going on there? So okay, so I guess you already seen the result. I'll run it. Actually, it took quite a while. Right. Oh, actually, I got a warning. Oh my god. Or is it still doing? No. Oh, it's still running. Yeah, it's very slow, this one.
Because those are just strings, right?
Because it is a string. Because it is 1.93? So yeah. Wait. Oh, maybe because no. This is nanosecond. This is okay. So it's like an order of magnitude difference. Yeah. So yeah, you can see that it's slower when it's have the conversion of the type, because again it's even if you use JIT, right? So JIT will still try its best to help you. So when JIT see that, oh, actually you are just passing integer in, and it should be njit instead of JIT. Okay, I'll automatically do njit for you, so you will have it faster. But then like if it's something that can't be njit, that need to use object mode, can't be no Python, then it will be slower. So even though there are lots of scary warnings, so sometimes it could be a easy fix, because if even if you're using object mode, if it can be optimized, it will be optimized. So it's kind of Numba is trying its best to be smart and try to help you. So yeah, sometimes it's not a bad thing to use JIT if you're really struggling. If it's just that some people may want to have full control to make sure that nobody break this, it must be compiled, then njit will safeguard that for you. So another thing is it's empty list. So this one is showing the normal thing. This is not an empty list, so everything should be fine. Right, everything's fine. I can compile it. No scary warning. I can use njit. No scary warning. Everything is good. But if we do the empty list, as you can guess, this will give you a scary warning. Right? Can you guess why it is the case? Anybody already know what's going on here?
Contents of the list. You don't know what types.
You don't know what type it is. Yes, this is what Numba doesn't like, so it is even worse than this, right? Like this, for example, this, right? It's like only 2, so can kind of guess or something. But this really can be anything, right? It's empty list. You can put anything in it. You can even put your self-defined like a Python object. You can put a magic mock. You can put anything in it. So Numba really don't like it. So. This is a very, very, very difficult question, but how can you create an empty list, but you can still tell Numba what type it is, for example, integer? Yeah, this is a fun kind of exercise. Don't worry if you can't, because I already have the answer somewhere. You can load it and check it yourself. but I would give you maybe like 5 minutes to try it first. It's really something that, you know, you would get aha when you see the answer, but give it a try. See if your idea will work. I'll give you 5 minutes to try it. Who has confidence that they have got it? Ooh. It's fine. You can look it up because you know, we all look up things when we work, so it's fine. So, but anyway, this is the answer that I have written before, or actually, it's actually in the documentation. So if you paying attention, then you will find this. So this is, well, it's creating a list of integer, obviously, but the funny bit is like, is in a range of zeros. So basically, it's creating an empty list of integer. I don't know if Python can do that. Okay, range 0, I don't know. And I don't know that like it actually registers an integer because technically there's nothing in it. So it's mind-blowing. Yeah.
So I found in Stack Overflow, Numba had like a type dot list, and you can declare an empty list with a type.
You can do that as well. That may be actually,
So it's like a type hint of an empty list.
yeah.
built this Python typing thing and it didn't work. It only took the number.
Yeah, the
You have to
typing.
do the number.
Yeah, so I've talked to the maintainer saying like, oh, now everybody loves typing, right? How about Numba can understand typing? And then he said like, that's a good suggestion, but we don't have that in the near future. So please be patient. Or you can start contributing if you want to solve that problem. So yeah, so now actually other people are already having break. So let's have a break until 11:30 when, no, sorry, wrong. At 11 where everybody finished their break, then you also come back at 11. Is that okay? Good, yeah, okay, so. Go, you can meet up with your friend in another tutorial. They may be having coffee outside, you know, have some cookie. I don't know what they have outside, but come back at 11, and then we will finish the second part of the tutorial. Okay, it's about time we come back to the zone. So before I started, I want to do a survey, but this survey is relevant this time. Is who has done this tutorial actually? This tutorial, by the way, is actually from the NumPy documentation. It's about how to build a neural network from scratch to distinguish the MNIST dataset, which is the handwritten digits. Who have done this before? One person. Oh my God, you would be very fast ahead of us. But who have actually maybe seen this but haven't really gone into detail about this before? A few of you, okay. So since the majority of people hasn't done this before, I think what I'm gonna do is I'm gonna give you how much time? Maybe 20 minutes to go through this, and then I will spend some time just like speed run this, you know, so that like we kind of make sure everybody's on the same page. But I'm sorry for people who already have done it before, already know you can already, like maybe you can read it again just to refresh your memory, and then you can move on to 3.2. But otherwise, for the majority of people, I will give you 20 minutes to go through this tutorial. It's very good explanation there. It's just like, I think understanding what's going on will help you in the next exercise. That's why I think it's worth spending some time to do it, especially also loading the data as well. So yeah, spend some time on this, and then I would do a sum up and explanation right after, but I will let you try it yourself first. Okay? So it's about time. So I know that people are at different places, but unfortunately we have to finish the workshop. So what I'm going to do is I'm going to go through this quickly. I will point out a few things that we have to take note, but I won't explain all the detail of the mathematics and how, like forward propagation, back forward. I won't explain that because that would take a course to understand the neural network. So yeah, for those of you really interested but you don't have the time to finish, you can always come back to do this. I think this is really good, a very good explanation. And even though like maybe you haven't heard about machine learning and neural network and want to learn more, there's also online courses that you can do as well. So So this graph explains how it works. So it would be, you know, there's a hidden layer which is just matrix, and then there would be like, you know, it's a loop. So because every time it would calculate how much, like how far off the prediction is, and then it would try to improve itself by doing this forward and backward propagation thing, which is some mathematic steps, which I won't go into the detail. This also, I hope you already have the library, so it's not a problem. And then the MS dataset, like I said, is a handwritten digits, so they are black and white images, so or grayscale images. So how an image works is basically, you know, if you see it on the screen, it's a picture. But actually, if you know, look inside how big they are, you know, you pixelate it, you know, because each pixel is actually a value. So for grayscale image, actually, it's just showing that how dark, maybe like, you know, 000 is black, and then if it's like 255 is white. So it's just how dark that pixel is. So that's how we're going to interpret the image. So they are all like kind of, you can download them online and stuff. So it's using requests to grab them somewhere on the internet. So if you don't have good connection, it will take you a while. Yeah, just all this technical stuff. And then after that, then we have that image. So if you draw it on screen, it's kind of like that. It's pixelated again, like each value kind of represent how dark this pixel is. So these are all zeros, and this one probably 255, something like that. So all of them are actually like pictures, the handwritten image. So the goal is to see if we can build a neural network, which is kind of very basic form of AI, to see if we can determine this is a 3, this is an 8. We can do it perfectly, right, as a human, but can a computer see this? So this is, again, just showing the image, and because image is just, again, just a matrix of numbers like this. So yeah, it's just a bunch of values. At this stage, this is integer, so that you can see that now we do some processing, which like convert the integer into float. So this is a point that you have to maybe put a mental note in your mind that, oh, all these will be floating numbers. So we know the data type, right? So it may help you when you try to use compiling. So now they are kind of, we call them normalized, which is like from, because originally it's 0 to 255, now it's divided by 255, so it's becomes 0 to 1. So we kind of compress the range, and they become floating point numbers. So similar thing happened with the results. So the result, we do one-hot encoding, which means that it will be a vector. So if it's 1 and then all 0, then it's representing the digit on the picture is 0. If it's 0, 0, 0, and the last one is 1, mean that is a number 9 represented the picture. So that's called one-hot encoding. So which one it is. So basically, like if you imagine it's a checkbox, which one is check? Okay. So that's like that. So it's like you can see 0 and 1, all of them. That's because they're one-hot encoded. But because the data type need to match again, they become float for some reason. So you can see there's a dot there, which means that they're floating point numbers. So yeah, so this is the basics of what had happened. Now this is the scary bit, which is the neural network bit, which again, if you're very interested, look at this math. This neural network only have like 3 layers, 0, 1, and 2. And I think that number 2 is the result, and you compare that with the one-hot encoding or something like that. I may be wrong, though. You can look into the details. There's also the weight that is for forward propagation and things like that. Again, we'll skip the detail for now. These two actually are the functions that is used quite a lot in machine learning. So you will see this ReLU function in the spoiler. You will see this ReLU function soon. So pay attention to this. This is quite an important function. It's used in backward propagation. If you draw it on a graph, it's kind of like when it's positive, it's like this, and then negative, so it's like. So when it's negative, there's 0, and then positive, like it's just like a diagonal line. There's another function similar to ReLU, but it's just like 1 and 0, like this. Yeah, so basically this is used for, I think it's used for kind of seeing how wrong or how correct you are. It's useful to give feedback to your neural network to correct itself. That's why it's needed. So yeah, these two functions are quite tricky. So because they are not your normal function, they are if you know math, they are not smooth, right? They are like so funny. And then we have these are hyperparameters. You can change them when you do machine learning. You can fine-tune your model to make it better and change it, but we won't change them. We just leave it as is. The weight, so this is the starting point of where you start to train. So this is just an initialization. And then these are the steps that's doing your propagation, your training the neural network. So when you train a neural network, there will be loops. There will be, because every time, you will have a result and then compare the results to the correct answer, and then it will correct itself. So it's a looping thing. So loops. Then, take a mental note. This may be the part that we could improve with Numba. So, yeah. And then, originally, they will print out the result every single time. You will see that I kind of muted it when we go to the part, but I will explain more later. And then this is just plotting the progress of the training. So not related to what we are trying to achieve today, but if you're interested, they're there. Again, this is, I've just skipped them. It's for the other tutorial. So basically that's that. So how are we going to improve that? So if you really want, you can change this one, but I have made a simpler version for you in 3.2. So I copy some of the code from the original tutorial, and I have put them, delete all the explanation because you have it in the other notebook already. And so this is basically the same thing. So first step, loading the data. There's nothing much we're going to do that. It's just input, output, and things. So we won't use number on it. We just let it be whatever it is. One-hot encoding, we're also not touching it this time, so just run it. And it should be downloading something on my computer right now. Let's check. Is it doing anything? Oh, it's on the because it's on a it's on a further // so you won't see it here. It's somewhere. It's downloaded. I just trust it. I hope. And then build and train a small neural network. So this is the bit that is doing the training. So this looks familiar, but it's different. So, also I forgot to mention one thing here. One second, let me find that. That's quite important, but I forgot where I put that. So the original tutorial there, if you have gone through them already, then they are using only 1,000 examples in their training. So actually this one is very fast when you go through them because they only use a small sample size. So practically, a lot of times when you train a more sophisticated neural network, you will want to use more pictures and more images. So to make it more challenging for us to, basically making the algorithm not run too fast so we can't improve it, I have put more data in it. I think I put 5,000 somewhere here. You can change it if it's too slow for you. Here, 5,000. So if you want to, just give it the try first, you don't want to make it too slow, you can change it back to 1,000. But I will start with 5,000 for now. So, just the sample size is different. Here, this is where the machine learning thing works, and I'm not touching this. I'm just copying them and then making it into a new function. So you can see this code is different from the tutorial. I have made a new class, and then I have put all these forward propagation as a separate method, backward propagation as a separate method. You will see why very soon. It's kind of because, I will just explain myself. Because you see that this process is just in a loop, right? It's not in a function. If it's not in a function, we can't apply the JIT and NJIT decorator. We can't apply it to a for loop. So we have to write it into a function. And just for the ease of passing all these layers and variables, these need to be passed between these various functions. So I create a class for it. So all this weight and all these layers, value of the layers, they need to preserve during the training. So I put them in as a class. That's the main reason why it's written like that. They're doing the same thing, trust me. I've tracked the result, cross-checked the result before. So if you encounter anything weird, let me know. So they are all kind of structured. It's a very good start for you. If you want to use JIT and NJIT, it's already done for you. So you can start attacking them right away. But before we attack them, we want to do profiling. There's another name in the title, right? So we have to. So now we are doing some profiling. So how we do profiling? We use the very basic C profile to do that. Like I said, there's a lot of profiler available out there. If you have another favorite, then please don't be shy and use it. But I'm just using what comes with CPython. So here we are trying to do some profiling. Have I run the code before? I think I haven't run the code before. Let me run this. Okay. So it will take some time because I've upped the size of the sample. So this is kind of standard how you do it. But notice that, a few things to notice here. So when profile.enable, it will start profiling. Profile.disable, so basically start and end of the profiling process. So between these two is what I want to profile. So this one is, how the training. So I want to see all these different things going on in the training. And you will also, by looking at this, you will also see why I put them into different methods or functions like before. I will show you in a bit. But you will see that the statistic, how we display them, you can change it a little bit to play around, but what I do is I would sort them according to accumulated time. There are different things you can sort them with. You can sort them with how many times they're called, how many total times they are they have been spent to execute all these different things you can use, but I would use accumulated time. Feel free to change it. It's yours now. It's your experiment. You can play around with it. So this looks a bit scary. It's just because all this code are stored in a very funny place because of how IPython, Jupyter Notebook work. But what I would do normally is just look at the end of it. Usually it would just have the name of the function. For example, a module is just module with train. So train is the biggest one, right? So of course it's taking the most time because it's the mother of everything. So everything runs inside it. So it's taking the most time. But if you look at this, you can see back propagation, actually it's here, forward propagation is here. So if you compare the accumulated time of the backward and forward propagation, you will see that backward actually costs more, even though they are run this one, they are both run how many times? It's a bit difficult to see. So yeah, this is the time they have been called. So they have been called at the equivalent, so number of times, this is how many, it's 100,000 times, both back and forward prop. But the backward prop costs a little bit more time because of the process costs a little bit more time. There are also, of course, these have built-in things that you can't really do much about it, but try to look for these ones that you name and define yourself. Then you have a better idea. You can compare them to see which one get called more times, which one is taking more time, and all these things. If you want, you can also break this up more. This is, again, like I said, a starting point for you to compare and try to break things down, to investigate which one actually costs the most time and where to attack it to, reduce the time that it took. So, if you want, you can also maybe break down these steps a little bit more so you can maybe see better, or maybe later when you use JIT or NJIT, then you can have a more detailed control of what you are compiling. So this is how it works and how you interpreted it, right? So it's just a very, cover the basic of profiling again. It looks a bit scary, but look for the ones that you define, and look for the time, which one costs more time, then maybe that one you should worry more about. So after that is your time. So now I have add to do here, which means that I haven't done anything yet, so it's your time to do things. I created another class so they don't overlap each other. So within that, again, you can change stuff. You can decide which one you want to use the decoration. You can choose JIT or NJIT. I would say that try NJIT and see which doesn't work, then you can use JIT, but then I would challenge all of you to try to just use NJIT. Maybe it will take you a week or a month, but you don't have to do it today. You just get a taste, try your best to see how much you can improve, and then we profile it again. Then you can compare the process, like how much improvement you got compared to the first one when you profile, or does it really, worth the effort to rewrite it and make it faster? How fast you can go? So yeah, all of them are open questions. So it's now your time to try it. At the end, I put the rest of the code in one cell so you can compare the result with the previous one. You can see that the neural network is not very good if you use a huge amount of sample. The original tutorial have optimized everything, but you can change the sample size for your liking and just to see which one can make it faster. So to have a better result, so you may wonder, like, oh, how can I get better result with more samples? You may have to change the hyperparameters. So that bit I won't go into detail because we are here to make it faster, not to make it more accurate. Well, ideally, you want to make it more accurate as well, but then you have to put another effort to change the hyperparameters. So so now is a free time to try and do stuff, ask questions. If you want, if you already kind of talk to your neighbor, you have make friends, then you can work together maybe. So now how much time we have? We have around, so slightly shine than an hour. So you have plenty of time. Try to challenge yourself. This is your hands-on exercise bit, and ask questions. So we have around 15 minutes until the end of the tutorial. You of course, feel free to stay and then work till the very, very end. Or if you have questions, this is your last chance, ask me questions. But if you, for example, have questions in the future, my DM on Twitter is open, or you can find me on LinkedIn and drop me a message. And I would genuinely, if I can help, I will help you. But sometimes, I may have to direct your questions, or if you can have a very clear question, then I can just put it, direct it to someone who can help you. Here's my contact, and also the other thing I want to tell you is EuroPython, which is again maybe not as big as PyCon US, but also quite big conference in Europe. There will be other maintainer, other developers there that you can meet. If you are based in Europe, or if you are want an excuse to go to Europe, this is your chance. It's going to be somewhere in Prague. It's going to be a very nice place to be. It's beautiful. I think that's it from me. Oh, also one last thing. Since I work for Alaconda, we'll have a booth. The opening will be later today, so please stay around and come to our booth. We'll have demonstration. We'll have PyScript people there. We'll have Conda people there. We'll have people who also show you how to do your data science work on the cloud and things like that. So please come and have a look. I may be there as well. So I hope you enjoy the rest of the conference. And it's not the end. You can still ask me questions. I'm just going to announce it in case some people want to leave earlier. But thank you so much for coming. Oh, by the way, they may also ask you a questionnaire to give me feedback. So all the feedback are very welcome. But if you don't like anything, could you please maybe mention a small thing that you like? So it's not just like last year, the questionnaire was quite... people are very honest. So, I welcome feedback, but if you, think that's something I have to improve, maybe mention a small thing that you like first to make me feel better. That would make me feel happier. But anyway, thank you so much for coming, and I'll be here answering your questions till the very end. So, thank you.